welcome to TryRide, the new era of learning. It is Pack 365. In Module 2, we are discussing about Iterative Deepening Depth-First Search, IDDFS algorithm in AI. Part A. Let's continue the topic. We call it as IDS and IDDS because it has both names. We can call like that also. Iterative Depending Search we can call, or Iterative Depending Depth-First Search also we can call. So, we have a simple conclusion here. There are two common ways to travel a graph, right? We have BFS and we have DFS. Considering a tree or graph, a huge height and width. Both BFS and DFS are not very efficient due to following reasons, right? What's the reason? Let me check it. So, breakfast search. BFS goes level by level but requires more space. The space required by the DFS is OD, where D is depth of the tree, but space required by the BFS is ON, where N is the number of nodes in tree. Y. Note that last level of the tree can have around N by 2 nodes and second last level N by 4 nodes. And in BFS, we need have every level one by one in queues, right? So, in BFS, we generally travel level by level, right? So, like not in-depth level by level, just we consider level by level. Like, if we can start with starting node with A, and we represent move to the B, and we move to the C again too. We complete the both nodes, and we complete the next node, right? We don't know. Like we develop, if we have we can come to BA, we have complete to a B node, and we start with C node. Like again B node and complete the C node. Like we comes to set of level by level. So it's simple, inconvenient with this iterative. And now check DFS. DFS first travels nodes going through one adjacent of the route, then next adjacent. The problem with these approaches is if there is a node close to the root but not in first few subtrees explored by the DFS, then DFS reaches that node very late. Also, DFS may not find shortest path to a node in a term of number of edges. So, depth first search is almost it directly it does not travel shortest distance, right? It does not see the shortest path and neighbors. It directly enter into the deeper. If we start with A, the A tagged with B, after it doesn't see it has C or D, it directly jumps to the subtag of the B of which is has, right? Sub neighbor. It directly enter to the in deep first nodes from starting line. Okay. So it has some uncanniness. So we did not proper it does not consider any proper iterations in this too in a heavy, huge, complex data set. So that's why we introduced iterative depending depth first search. Okay, in it we have iterative depending depth first search IDDFS is an ununified search algorithm that is used to explore or search through a graph, right? So it is a graph search algorithm that combines the benefit of depth first search and breadth first search, both BFS. It is particularly useful when dealing with a large graph or when a depth of the solutions is unknown, right? So the main core idea of the IDDFS, the fundamentals idea behind the IDDFS is to perform a series of depth limited depth first, right? DLDF, we can say DLDFS, like depth limited depth first search, gradually increasing the depth limit in each iteration. So it rise a leveling of the nodes. The key features of the IDDFS is the iterative approach, where the depth limit of the progressively increased during each iterations. So we can see here we have increased each iteration increased like node to node. So this method combines the memory efficiency of depth first search DFS with the completeness and optimality properties of the breadth first search. So we can say here memory efficiency, like we have that. So DFS is known for its low memory usage, right? Because it only need to store the current path from the root to the current node. And IDFC retains this advantage as each individual DLDFS is efficiently as DFS. So when it comes to completeness of like BFS, BFS is a complete meaning. It is it will always find a solution if one existed, right? Where IDDFS achieves completeness because the progressive increasing by depth limit, it will eventually reach the depth at which the shortest path to the goal lies. So IDFC is a particularly effective for the large graph where the depth unknown potentially infinite. So we can say optimality like a BFS for unweighted graph. So we can see here in unweighted graph where all the edges or close all the edges cost are uniform, right? BFS find the shortest path. IDDFS also find the shortest path because it explores all the nodes at the given depth before moving to the next deeper level. The first time it finds the goal and it gradually to be moved shallowly possible to the it tries to make to efficiently make to try to depth in the depth move in depth effective for unknown of the infinite depth when we say when the depth of the goal node is unknown or a graph like in potentially infinite, right? Potentially infinite where IDDFS is a good choice unlike a pure DFS which might get stuck exploring a deep unproductive path. IDDFS ensures that all the shallower paths are explored first. So we can see here performance sequence of depth limit search like it perform order to level by level ordering with increasing the depth limit like level 1, level 2, level 3, level like that. And sounds wasteful. Each iteration repeats all the useful work of the previous iterations. In fact, overhead acceptable. We have analysis follows. So here we have iterative depending differs a simple logic sample example of a code. Like if you use the for depth limit 0, 1, 2, 3, the depth limit it starts it has in so it starts from the solution of the 1, 2, 3. First it takes 0, start to 2, like level it increase the level by level. So it returns some kind of iterations like level iterations. So it has common advantages of bid first search and bid first and depth first search. Okay, so BF it has a common advantages with the DFS and BFS both, almost like BFS semi complete, however not complete, right? Like BFS, optimal if all actions have same cost. Like DFS only need to store nodes along a one path, space complexity. Oh, we have here and where D minimal solution length and we have time complexity too. And we can see here start how to start the iterations. Like we have initialization depth limit, set the initial depth limit to 0. So the algorithm begins the settings the depth limit to 0. This means in the very first iteration, it will only check if the starting node itself is the goal or not. Step two, perform a depth limit depth first search like DLDFS from the starting node, restrictingly the search to the current depth limit. In the DLDFS, the search is confined to a minimum depth and nodes beyond that depth are not considered, right? DLFS is executed for the starting node. The, uh, the crucial aspect is that here is that the search strictly configured to the current depth limit or any nodes that would be explored by beyond the depth limit, right? Or ignored for the specific iterations. Think of it like this: if the depth limit is 2, the DLDFS will be one explored node at depth 0 only. The depth 1, depth 2 was ignored. Okay. Step 3. If the goal node is encountered during the DLDFS, returns the path from the starting node to goal node. Like check for the goal node. During the DLDFS, if the goal node is found at the any point within the current depth limit, the algorithm immediately returns to the path and start node from the goal node. This means the solution is been founded. Step 4, we have if the goal node is not found within the current depth limit, increase the depth limit by 1 and repeat the step 2 and 3. Like we can see here if the goal node was not found within the current depth limit, like meaning the DLDF completed without success, right? The depth limit is increment by 1. Then the algorithm repeats step 2 and step 3 with the new increment depth limit. This iterative depending is what gives algorithms its names, like it efficiently explores the graph layer by layer and by using a depth first approach for each layer. uh, So if the goal node is not found and the depth limit existed, predefined and maximum depth or depth of the tree, right? So terminate the search process. Like the search process terminates under two conditions. If the goal node is still not found, like we have two condition, what minimum predefined depth and the depth of trees. Like if there is depth limit existed or predefined and maximum depth, we can say that this prevent infinite loop. A graph will circle or a very deep unconstrained path. Depth of the tree, like if the depth limit existed exceed the um, actual maximum depth, like of the entry level. So the entry tree or graph, meaning all the recapable nodes have been explored up to the maximum depth it reaches. So we have like this, and the simple pickup is nothing but here we can see a graph. So you may choose, it is a point which we can check and imagine we searching like something a tree, right? We have a graph. So we have source node here and we have goal node, right? We starting study A. So in level A, we start from A, and in level, when it comes to level one, iteration zero, we start from A, right? And iteration two, it comes from, we start from B and C. Then we iterate that A, B, C. We complete the nodes by level. Like this, we have to complete the nodes. If it starts from here, right? If it starts from here, it is level one. We take A and B. In level two, we start from here, right? So if we comes with level two, we take A and we go back to A. We take B and go back to A, and we go back. I come back to C, like that. What's the possibility chances I have here? I come A to B, A to B, and C. So what is the possible chances I return to, again I come back to D, and I go back B, and I back E, and back to B, and back to A, and back to C, and back to F, and back to C, and back to G, and back to C again, and back to A, and come to again D. So this like iteration I may found like first I will initial state is my A, and after that my initial state is B. From B I have neighbors called D, F, right? I come up for DE. I complete the DE iterations first. Then after directly move to A. I directly move to A, and I because I directly move to B and A. B and A is already my existing neighbors, so I directly move to the next part C. And here C2 I consider F and G, and go back to again my parent C and A, parent nodes G and A. Then I start iteration. Like the next iteration like this, it happens. Like if the next iteration up to I want to find the goal node. It is currently repeated like this. So I found a G. If it is my root node is J, like means I want to travel like here, like this. Like this I want to travel. Like I am coming like this, so I complete this path to this path and this path. Like this I want to travel my graph. Okay, I hope you guys understand. Now, let's check iterative depending. Let's start with the iterative depending as example. So I have depth limit 0. So generated in the round 1, and total generated. How I start with 1. Like we have 13. So we have start with the point 1, and we want to move left and right. So I move left again. So my generator around 14, and total generator I 1. I started only 1. So I moved left, right. Again, I want to move right. I want to consider, I completed the level one and level two depth. So in level two, depth limit two, I already completed level one and level two, right? So I start from the level existing from the left side of left side nodes. I want to start here. And after that, I complete the left side, all left side neighbor of left and right. And then I move to right side of the neighbors. Then I want to complete the right side neighbor left and right. Okay. So in the level 3, I want firstly I completed left and right of the left both neighbor side. So now I complete with now here my iteration table is he begin. So from here I am making that. So this is my left, this is my right. So from here I am making another route left. I start one another route left and again right, again left, again I comes to the right, again right to left, again right to right. I complete again I come back to the whole. I change the whole directly next node. Right node, complete to first parent right node, and from that left and from that right, sorry, left again right, I reach my goal. So, like the example pattern will be behave like the pattern will be checked. So here I have here my generated rounds as 12 rounds I generated for this, and total generation is 1, 3, 4, 7. Like I have 7 to 12. So I have find the solution. So time capability here have a simple example of complexity. So bit first search, iterative depth first search. I have a formula of 1 plus b square like that. So I have depth plus 1, it is formula. So I want an example, I have b equal to 10 and d equal to 5. So for the bit first search, I have a solution here for 110 plus 100 plus 1000 plus 10,000. So I get almost 1,11,000 like that. So it is depending to, here also I get the 1,23,000. 456. So here we can see the time capacity of the theta. Let's B with the branching of the factor and B D with the minimum solution length of the given state space. Let be greater than or equal to 2. Like that we calculate the time capsule ca complexity here. And here evolution iterative depending DFS is often that method of the choice if tree search or in here tree search is educate, right? No duplicate eliminations necessary. All the actions cost and are identical, and the solution depth is unknown. Here conclusion, the summary. We can see here depth first search here. Expand nodes in LIFO, like last in first out. Order usually has a tree search. Easy to implement recursively, very memory efficient. Can be combined with iterative depending to copy combine many of the good assets of the best first search and the depth first search. We combine it with both. So I hope you guys all of you understand about the uh, topic of iterative depending depth first search IDDFS. So thank you all of you.